Welcome to this in-depth exploration of the Single Electron Transistor, or SET. This is one of the most fascinating devices in nanoelectronics, where we control individual electrons using quantum mechanical effects. Let's start with the fundamental question. What exactly is a single electron transistor? A single electron transistor is a nanoscale device that can control the flow of electrons one at a time. Unlike conventional transistors that handle millions of electrons, the SET manipulates individual electrons. It operates based on quantum mechanical tunneling through a tiny island called a quantum dot, which is connected to source and drain electrodes through tunnel barriers. For this to work, the device must be extremely small, typically less than 10 nanometers, so that quantum effects dominate over classical behavior. Here's the basic structure. We have a quantum dot in the center, which is a tiny island of conducting material. On either side are tunnel barriers that electrons can tunnel through. Beyond those are the source and drain electrodes. Below is a gate electrode that controls the electrostatic potential of the quantum dot. The key physics that makes the SET work is called the Coulomb blockade effect. Let me explain this crucial concept. When an electron tunnels onto the quantum dot, it has to overcome the electrostatic charging energy. Because the dot is so small, adding even one electron costs a significant amount of energy. The charging energy is given by E sub c equals E squared, divided by 2c, where E is the elementary charge, and c is the capacitance of the quantum dot. For nanoscale quantum dots, this charging energy can be much larger than the thermal energy kBt, where kB is Boltzmann's constant and T is temperature. When EC is much greater than kBt, we observe the Coulomb blockade. Electrons are blocked from tunneling onto the dot unless specific energy conditions are met. Let's calculate the charging energy for a realistic quantum dot to see why cooling is necessary. A typical quantum dot might have a capacitance of about 10 to the minus 18 farads, which is 1 attofarad. This is incredibly small. The elementary charge is 1.6 times 10 to the minus 19 coulombs. Plugging in these values, EC equals 1.6 times 10 to the minus 19 squared, divided by 2 times 10 to the minus 18. This gives us 1.28 times 10 to the minus 20 joules. Converting to electron volts, this is 80 millielectron volts. This is a substantial energy at the nanoscale. At room temperature, which is 300 Kelvin, the thermal energy kBt is only 26 millielectron volts. Since the charging energy is about 3 times the thermal energy, we need to cool the device to very low temperatures, typically below 10 Kelvin, for clear Coulomb blockade behavior. Now let's discuss the different implementations of single electron transistors, starting with quantum dot-based devices. Quantum dots are tiny islands of semiconductor material, typically made from materials like gallium arsenide or indium arsenide. These dots are typically 5 to 20 nanometers in diameter, small enough that quantum confinement effects become important. Here's a schematic of a quantum dot. Electrons are confined in all 3 dimensions. The dot is surrounded by tunnel barriers, often made of aluminum gallium arsenide, which have a higher band gap than the dot material. Because of quantum confinement, the electrons in the quantum dot occupy discrete energy levels, much like electrons in an atom. This is why quantum dots are sometimes called artificial atoms. For a simple model, the energy levels scale as En equals h bar squared, n squared, divided by 2 meters star L squared, where h bar is the reduced Planck constant, m star is the effective mass, L is the dot size, and n is the quantum number. The gate voltage can tune these energy levels up and down relative to the chemical potential of the source and drain. This allows us to control when electrons can tunnel onto the dot. One of the most striking features of SETs is the phenomenon of Coulomb blockade oscillations. Let me explain this. As you sweep the gate voltage, the current through the SET oscillates periodically. These are called Coulomb blockade oscillations, or Coulomb peaks. Here's what the current versus gate voltage looks like. You see periodic peaks, separated by regions of zero current. Each peak corresponds to an additional electron tunneling onto the quantum dot. The spacing between peaks is delta 5 G equals E divided by CG, where CG is the gate capacitance. This gives us information about the device geometry. Each Coulomb peak represents the dot going from n electrons to n plus 1 electrons. The values between peaks are the Coulomb blockade regions where the electron number is fixed. Now let's turn to nanowire-based single electron transistors. These are one-dimensional nanostructures that offer unique advantages. Nanowires are crystalline semiconductor structures with diameters ranging from 10 to 100 nanometers and lengths up to several micrometers. Common materials include silicon, indium arsenide, indium phosphide, and gallium nitride. These can be grown using techniques like vapor-liquid-solid growth. In a nanowire SET, the quantum dot is formed within the nanowire itself, typically by creating tunnel barriers through local gates or by introducing defects. The entire device is essentially one-dimensional. Nanowire SETs have several advantages. They have strong electron confinement due to the one-dimensional geometry. They can be grown bottom-up with high crystal quality, and they allow for easy integration with external electrodes. Here's an important question. Why do nanowires show such strong quantum confinement? The answer lies in their geometry. In a nanowire, electrons are confined in two perpendicular directions, but free to move along the wire axis. This reduces the available density of states and enhances quantum effects. The energy levels depend on two quantum numbers n and m. The energy equals h bar squared over 2 meters star times the sum of n squared over Lx squared plus m squared over Ly squared, where Lx and Ly are the transverse dimensions. In very clean nanowires at low temperatures, you can observe conductance quantization. The conductance occurs in integer multiples of the quantum of conductance. The quantum of conductance is G0 equals 2e squared over h, which is approximately 77.5 microsiemens. The factor of 2 comes from spin degeneracy. Now let's explore the third implementation, nanomembrane-based single electron transistors. This is a more recent development. Nanomembranes are ultra-thin two-dimensional sheets, typically 1 to 100 nanometers thick. They can be made from semiconductors, metals, or two-dimensional materials like graphene. A key advantage is that nanomembranes can be released from their growth substrate and transferred to arbitrary substrates, including flexible materials. In a nanomembrane SET, the quantum dot is typically defined by etching a constriction in the membrane. The thinness of the membrane ensures strong coupling to the gate electrode below. Examples include silicon nanomembranes, which can be thinned down to just a few nanometers, graphene monolayers, and transition metal dichalcogenides like molybdenum disulfide. Graphene-based SETs are particularly interesting because graphene is a zero-band gap semiconductor with extremely high mobility and unique Dirac cone dispersion. In graphene, the energy dispersion is linear, E equals h bar times versus F times K, where versus F is the Fermi velocity, about 1 million meters per second, and K is the wave vector. Let me now present the key equations that govern single electron transistor operation. These are essential for understanding device behavior. The total energy of the system with n electrons on the dot is E total equals E C of n plus E gate of n. The first term is the charging energy, the second is the gate energy. The charging energy is E C of n equals Ne minus Q0 quantity squared divided by 2C sigma, where Q0 is a background charge and C sigma is the total capacitance. The gate energy is E gate of n equals negative NeVg times Cg over C sigma, where Vg is the gate voltage. By plotting the conductance as a function of both gate voltage and source drain voltage, we create what's called a stability diagram. This reveals the charge states of the quantum dot. The stability diagram shows diamond-shaped regions where the electron number is fixed, separated by lines where current can flow. This is one of the signatures of Coulomb blockade. To understand the current through an SET, we need to consider the tunneling rates between the dot and the electrodes. The tunneling rate is gamma equals 1 over E squared RTC, where RT is the tunnel resistance and C is the capacitance. Typical values are megahertz to gigahertz. The current is simply I equals E times gamma effective, where gamma effective is the effective rate at which electrons tunnel through the entire device. There are two main transport mechanisms, Sequential tunneling involves electrons hopping one at a time through the dot. Co-tunneling is a higher-order process where electrons virtually occupy the dot. Here's a critical question. What determines the minimum temperature at which an SET can operate? The answer is that the charging energy must significantly exceed thermal energy fluctuations. We need EC to be at least 5 to 10 times kBT for clear operation. For our earlier example where EC was 80 millielectron volts, the temperature must be less than EC divided by 10 kB, which is approximately 100 Kelvin. Now let's discuss the applications of single electron transistors. Where can we use these remarkable devices? SETs can be used as ultrasensitive electrometers to measure tiny charges. They can detect charge changes smaller than 1% of an electron charge. In quantum computing, SETs can serve as charge qubits, where information is stored in the electron number. They can also be used to read out spin qubits in quantum dots. SETs can function as single photon detectors. When a photon is absorbed, it creates electron-hole pairs that change the charge state of the dot. In metrology, SETs are being developed as a new current standard based on counting individual electrons. This could redefine the ampere. If we can clock electrons through an SET at a precise frequency f, the current is simply I equals E times F. For a frequency of 1 GHz, this gives about 160 picoamperes. Despite their promise, SETs face significant challenges that have limited their widespread adoption. The most significant challenge is that SETs require cryogenic temperatures, typically below 10 Kelvin. This makes them impractical for most commercial applications. Random fluctuations in background charges from nearby defects or impurities can shift the Coulomb peaks and cause device instability. Higher-order co-tunneling processes can allow current to flow even in the Coulomb blockade regime, reducing the on-off ratio of the device. SETs have very small current drive, typically picoamperes to nanoamperes. This makes them difficult to integrate with conventional electronics. The holy grail of SET research is achieving room temperature operation. What would this require? For room temperature operation, we need the charging energy to exceed 10 times kBT at 300 Kelvin. This means EC must be greater than about 260 millielectron volts. Using our charging energy formula, this requires a capacitance less than about 0.3 attofarads. This is extremely challenging to achieve. The required dot size is approximately L less than 3 nanometers. This is close to the size of a few atoms, making fabrication extremely difficult. One promising approach is to use individual molecules as quantum dots. Molecules like fullerenes or carbon nanotubes naturally have the right size scale and can show Coulomb blockade at higher temperatures. Let's compare the three implementations we've discussed to understand their relative advantages and disadvantages. Quantum dot SETs offer the most precise control over parameters. They're ideal for fundamental physics studies and quantum computing applications. However, fabrication requires complex lithography. Nanowire SETs benefit from bottom-up growth, which gives excellent crystal quality. They can be grown in large arrays for parallel processing. The challenge is making reliable electrical contacts. Nanomembrane SETs are the most flexible literally and figuratively. They can be transferred to any substrate and integrated with flexible electronics. However, etching very small features in thin membranes is challenging. Let me briefly mention an advanced phenomenon observed in SETs, the Kondo effect. When the quantum dot contains an odd number of electrons, there's an unpaired spin. At very low temperatures, this spin can interact with the conduction electrons in the leads. This creates a many-body correlated state called a Kondo resonance, where the dot spin is screened by a cloud of electrons from the leads. The characteristic temperature is the Kondo temperature Tk, which depends on the tunnel coupling gamma and the on-site Coulomb repulsion U through this exponential formula. The Kondo effect appears as an enhanced conductance peak at zero source drain voltage right in the middle of the Coulomb blockade valley. This is a beautiful example of quantum many-body physics at the nanoscale. If you wanted to fabricate an SET, what practical considerations would you face? Fabrication requires an ultra-clean environment. Even a single dust particle can ruin a nanoscale device. Class 100 or better clean rooms are necessary. To create features below 10 nanometers, electron beam lithography is typically required. This is slow and expensive compared to optical lithography. Tunnel barriers are often deposited using atomic layer deposition, which allows control at the atomic monolayer level. Aluminum oxide is a common material. Measuring SETs requires dilution refrigerators that can reach temperatures below 100 millikelvin. These systems cost hundreds of thousands of dollars. What does the future hold for single electron transistor research? Researchers are exploring hybrid devices where SETs are coupled to superconducting circuits. This combines the charge sensitivity of SETs with the quantum coherence of superconductors. Another exciting direction is using topological materials to create SETs that host Majorana zero modes. These exotic quasi-particles could enable topologically protected quantum computation. Two-dimensional materials beyond graphene, like transition metal dichalcogenides and hexagonal boron nitride, offer new platforms for SETs with tunable properties. There's growing interest in integrating SETs with silicon photonics to create electro-optic devices that can control light at the single photon level. Let me summarize the key points we've covered about single electron transistors. Single electron transistors are nanoscale devices that control individual electrons through quantum mechanical tunneling and the Coulomb blockade effect. The three main implementations, quantum dots, nanowires, and nanomembranes, each offer unique advantages for different applications. The fundamental requirement for operation is that the charging energy EC must significantly exceed the thermal energy kBT. Current applications are limited by the need for cryogenic temperatures, though research continues toward room temperature devices. SETs hold tremendous promise for quantum computing, ultrasensitive sensing, and precision metrology despite the technical challenges. Ultimately, single electron transistors represent our ability to exercise quantum control at the nanoscale, manipulating matter one electron at a time.